Hi, I am Sanjay Patel. We have studied the concept of double integral and also the notion of repeated or iterated integrals in our previous lectures. So far we know only how to compute the double integral over a rectangle by different methods. Now we are interested in understanding how to compute the double integral over a closed region. That region can be any irregular shape, say something like this. Means our function is defined on some region like this, say in R2. Okay, this is x-axis, y-axis, origin, and this is our say region E, and a function is defined from say E to R. So f is a function of two variables. Okay, and E, this E, closed and bounded region E, is a subset of R2. It is a subset of R2. So you want to understand how to compute the double integral of the function f of two variables over the irregular closed region E. This is denoted by double integral f of x comma y dx dy over the region E. So this is the main say thing of today's lecture. In this regard, we have an important theorem about double integral over a closed region. So let us write down the result. So it's a theorem. Say let f from E subset of R2 to R, E subset of R2 to R be a function of, rather a continuous function. Let me take f from E subset of R2 to R be a continuous function of two variables x and y, which is defined on the region, the closed and bounded region, capital E, okay, which is bounded by the curves y is equal to phi of x and y is equal to psi of x, where phi and psi are any functions of x and they are also continuous with say phi of x is less than or equal to, rather strictly less than, let me write, where phi of x is strictly less than psi of x for every x belongs to some closed interval a b. So this region is bounded by the curves y equal to phi x and y is equal to psi x, and also the lines x equal to a and x is equal to b. Okay, then since the function is continuous, this double integral exists, then the double integral of this given function f over the region E, which is denoted by f of x comma y dx dy over the region E, can be say evaluated using these iterated integrals. So this can be evaluated as integral x is equal to a to b, okay, and integral y is equal to phi of x to psi of x, f of x comma y dx comma dy, or we can write, or we can compute this double integral over the given region E using the other repeated integral, and that I can write as y is equal to c to d, x is equal to phi y to psi y, f of x comma y dy comma dx. Okay, let me write this as an extra thing which I will explain later on. So the double integral of the function f can be computed either using this iterated integral or this iterated integral. So there are two results, but I am going to prove only this part, the first one. Okay. You know the other notation for this repeated integral, you can write as x is equal to a to b, which we simply write without mentioning x. Say a to b dx, and say phi of x to psi of x, okay, f of x comma y dy, and this is the limit of y, and this is the limit of x. So x is equal to a to b and y is equal to phi x to psi x. So let us prove this. Here the region E is a closed and bounded region which is bounded by the curves y equal to phi of x, y is equal to psi of x, and the straight lines x is equal to a and x is equal to b. So it is enclosed between these four curves. Okay, and the function f is continuous function defined on this closed and bounded region, and therefore the double integral exists. What we want to prove is this double integral in this case can be computed using this iterated integral. So let us consider the proof. And let me draw the figure first. I have already prepared the figure, so I will just paste it. Okay. Here, our function is defined on this closed and bounded region. See, yes, it is defined on this closed and bounded region E, which is bounded by four things: the lines x equal to a and x equal to b, that is the vertical lines shown by pink color, and it is say just touching this region at the point A and at the point C, and we are given the two curves. One is the curve ABC, that's why I have taken this point, the curve ABC, which is given by y is equal to phi of x, and the other part of this region is given by the curve ADC. Okay, this ADC, and its equation is y is equal to psi of x. So the curve is bounded, the region is bounded by this curves. Let me so this A, you can say this ADC which I am highlighting by this orange color, this curve is given by the function y is equal to psi x. Okay. Since the region is enclosed between the four things, x equal to a, x equal to b, y equal to phi of x, and y is equal to psi of x, we can enclose this region in a rectangle. That means we can find these 2 points b and d where the lines the y equal to c and y equal to d exist, which touches this bounded closed and bounded region at b and d. So we can have a rectangle, and this rectangle, this whole rectangle, I want to name as a rectangle E dash. E is our region, which is shown by these blue lines enclosed between this curve, and this rectangle is including all these points here as well as here and here, and this, all these points together with this region E is our rectangle given by x equal to a, x equal to b. So this rectangle E dash is actually the rectangle AB cross CD. So because of the say closed and bounded region, we can do this thing. So let me write down this and say begin the proof. So since f from E subset of R2 to R is bounded by the four curves, namely x is equal to a, x is equal to b, these two lines, and y is equal to phi of x and y is equal to psi of x, with, we know the condition, phi of x is strictly less than psi of x for every x between a and b. And that you can see here in this figure also, that whatever x you choose anywhere, say here, that is between a and b, the corresponding value of the function phi is here, this is phi of x, and this for the same point the value of the function psi of x is here. So phi of x is strictly less than psi of x for any x between a and b. So that is the say given condition. Okay. Since the function is bounded by these curves, we can enclose the region E into a rectangle, okay, say E dash given by AB cross CD. Okay, that I have already explained. So that means the region E is contained in the region E dash, where E dash is a rectangle and E is the given closed and bounded region. See here. Okay, so rectangle means this complete region, while E is only the blue shaded region. Okay, now what I want to do is I want to define a new function on so I want to define a new function which I will call capital F. So define a function capital F on the new rectangle, that is E dash to R, as follows. And my definition of the function is f of x comma y is equal to f of x comma y is equal to, say, f of small f of x comma y if the point x comma y belongs to the region E. And we define the function value capital F as 0 if the point x comma y belongs to, say, E dash minus E. Let us understand what is the meaning of this. So I am taking a new function capital F whose value at any point xy in this rectangle, if the point lies here, let me choose some nice color. Yes, if the point x comma y lies here in E, then the value of the function capital F I would like to take as same as the function small f of x comma y. And if the point is here outside of this region, that is here or here at any of these four places, then I want to take the value of the function say f of x comma y as 0. So these are the two formulas for the function capital F. And since the function small f, which is defined over the region capital E, is continuous, and function is also constant in the remaining part, function is continuous everywhere. So since the function is continuous, let me write here, as small f is continuous on the region E, by definition of the function capital F, it is continuous. I mean, the function capital F is continuous on the rectangle E dash. So this implies the function capital F of x comma y is integrable on E dash, means on the rectangle E dash, which is given by, it is closed interval AB cross CD. And if the function f is integrable over a rectangle, then we know that its double integral is given by, therefore the double integral of the function capital F over the rectangle E, over the rectangle E is rather E dash is given by f of x comma y is equal to, say, over the rectangle, let me write this way, since capital F is integrable on E dash, so we can write the double integral of the given function f of x comma y over the region E, the double integral of this function, this is same as the double integral of the function capital F of x comma y dx comma dy, over the rectangle E dash. Remember, since the function is 0 for every point in E dash minus E, we can write the integral value of the function small f over the given closed and bounded region E, same as this integral of function capital F over E dash. So this is equal to, I can write, since the function is integrable over E dash and E dash is a rectangle, I can write this integral as x is equal to a to b, it is bounded by the two lines, and y is equal to, say, c to d, capital F of x comma y dx comma dy, by using this iterated integral. Functions capital F is integrable over E dash, so this double integral is written by this. And these two are same because capital F is 0 for every xy belongs to e dash minus e. Now I want to simplify this to show that it is equal to the required repeated integral. So let me write the meaning of this iterated integral, that is integral x is equal to a to b. Okay, this is first integrated with respect to y and then with respect to x. Integral y is equal to c to d capital F of x comma y dy, and here it is dx. Okay, so this is equal to integral x is equal to a to b, and then we can say consider we are keeping the value of x fixed here and integrating with respect to y. So when x is fixed, how does y change in this region? So it changes from, say, c to, let me explain in the figure, that x is fixed. If you take any point x here, when you keep it fixed, then the y value changes from this point, which is y equal to c, to this curve, which is y is equal to phi of x, and then it changes from y is equal to phi of x to y is equal to psi of x. Okay, or it can be here also. If it is somewhere here, say if x is somewhere here, then x changes from c to d, and then phi x, c to phi of x, then phi of x to, say, psi of x, and then psi of x to this green line, which is y is equal to d. So therefore I can split my this last step, this integral y equal to c to d capital F of x comma y as this way: c to d y is equal to c to phi of x, as I explained, capital F dy, plus y is equal to phi of x to psi of x, capital F dy, plus y is equal to psi of x, to d, capital F dy, and then let us close this. This is to be integrated with respect to x then. So we have written this integral as a sum of these three integrals. Okay, and you know very well that the function capital F is 0 at this and these points between y equal to c to phi x and y is equal to psi x to d. The function capital F is 0 because c to phi x is this region where the function is 0. Here the function is 0, and from psi x to d means this region. In psi x to d also the function is 0. So at all these points the function capital F is 0. So these two integrals are 0. So this is 0 and this is also 0. So I can write this as integral x is equal to a to b, say y is equal to phi of x to psi of x, capital F of x comma y dy, and this is dx. But what is the function capital F between y equal to phi of x to psi of x? It is same as, according to definition of capital F, it is same as the function small f, because in this region E, that is between phi x to psi x, the function capital F is same as the function small f according to our definition. See this definition here in the region E, this capital F and small f are same. So I can replace this capital F now by function small f. This f is replaced by small f. So this is equal to x is equal to a to b, and then y is equal to phi of x to psi of x, small f of x comma y dy, dx. Okay, because capital F is equal to small f for every x y belongs to capital E. Okay, so this is proved that this double integral of small f over the given region E is equal to this thing, which is nothing but the required iterated integral. So thus we have proved that the double integral of small f, the function small f dx dy over the given closed and bounded region E is equal to this thing. But what is this? It is nothing but the repeated or iterated integral given by x is equal to a to b dx and y is equal to phi of x to psi of x f of x comma y dy. Okay, so the theorem is proved. The same way you can obtain that other repeated integral of this double integral. So let me write, hence the theorem is proved. Hence the theorem is proved. Okay, we'll see some examples in our next lecture how to compute the double integral over any closed and bounded region, and that is the most important topic. But before that, I want to mention some result, something like working rules of double integrals. You can say working rules of double integral. And this I am going to write for any closed and bounded region. Okay, so the rule says if f of x comma y and g of x comma y are integrable, in the sense that the double integral exists, are integrable over a closed and bounded region, a closed and bounded region, or over a region, closed and bounded region, yes, then we have the first working rule, like let us say double integral of f plus or minus g over s dx dy is equal to double integral of f dx dy over s plus double integral of g, or plus or minus double integral of g dx dy over s. The second result, double integral of k times f of x comma y dx dy over the region S is same as k into double integral f of x comma y dx dy over s. Okay, then the third result I can write as if f is integrable, we have assumed in this theorem or in this result, if f and g are integrable, if f is integrable function, then both the repeated integrals, say this is the important thing, both the repeated integrals exist and they are equal. So this and this, whether you change the order, you will get the same value, dy dx. Okay, and the fourth result I want to mention here is very, very important for solving the problems of double integral over closed and some irregular regions. Suppose, uh, suppose the region S is made up of some two regions or say more regions, some finite number of regions satisfying this condition that S is equal to S1 union S2 and say S1 intersection S2 is equal to phi. So region S is a union of two subregions, say S1 and S2, which are disjoint. Okay, so something like this. I will explain it later. Then the double integral of the function f dx dy over S is equal to, this can be computed separately with respect to each of the region and then we can add. So this equal to double integral of f over S1 plus double integral of f over S2. So here the region will be something like this. So suppose this is a region and this is S1 and this is S2 and this whole thing is our S. So S is equal to S1 union S2 and S1 and S2 are disjoint sets. Okay. And the last result is about mod of the double integral of f dx dy over the region S is always less than or equal to double integral is always less than or equal to the double integral over S of mod of f dx dy. Okay, so these are the simple rules about our double integrals over closed and bounded regions. So in our next lecture we are going to solve problems how to evaluate double integral over any closed region, and that is a very important topic. So till then, goodbye. Thank you.